Can everybody hear me? Hello everybody, my name is Sven Behnke. I work in the Computer Science Institute in Freiburg, and we are building there humanoid robots and try to make them do something non-trivial. And I'm glad that you all came here. Here's the outline of my talk. First, I would like to try to motivate you that doing research on humanoid robots makes kind of sense. I will talk about some projects worldwide that deal with humanoid robots, and talk a little bit about the new Humanoid League in the RoboCup competition that if you attended the previous talk, you already know. Our team is called Nimbro, and I have some of our robots here. I didn't bring Alpha because it's kind of big robot, but here RoboSapien, the Condor robot, and robot Tony are here, and I will talk a little bit about how we built them and how we program them. And at the end, I want to talk a bit about personal robots. I think there are two motivations for building humanoid robots. One is a very practical one, namely that there is a need for humanoid robots. These industrial robots that you see in the upper left, for instance, that are used to build cars, they do like 1,000 times each day the same movement, and they work in cages. So they are separated from humans to prevent damage. They are really inflexible. And if you want to apply robots in new domains, like in the service industry, or as a household helper, or for entertainment, then I think you need more flexibility, and a human-like body is helpful, especially when it comes to interaction with people. So a human-like body helps you when you act in a world that has been designed for humans, for us. And this becomes obvious once our body is disabled in some way. So if you go around in a wheelchair, you learn that it's not so easy if you don't walk on two legs. And robots that don't have hands, they might have difficulties opening a door because they cannot operate a door handle, and so on and so forth. Also for communicating with people. In our brains, when we grow up, there's a user interface hardwired, and this is a very intuitive one. So we speak with our hands, we speak with our body, we look through other people's eyes, we do all kinds of stuff that is different from the usual user interface of keyboard and screen. So I think this is a very intuitive user interface, and if it works well, you can program your robot just by doing what the robot is supposed to do by demonstration, and the robot then would be imitating what it has been seen, and this would be a very intuitive way of telling your robot what it is supposed to do instead of programming it. The other motivation comes from artificial intelligence research. In the last years, there has been a growing insight that intelligence needs a body. This is called embodiment, and it shows itself only through interaction with the environment, situatedness. And to foster this development, since 1997, the RoboCup Federation holds yearly annual competitions. So the federation managed to establish soccer as a new AI benchmark, kind of a successor of chess. And the characteristics are that RoboCup takes place in a dynamic environment, that states change in real time, you have only partial access to the information, your sensors deliver signals that you need to interpret, and there is distributed control. So RoboCup started with wheels robots, but now there is also a Humanoid League. And this approach, this motivation for building humanoid robots is using them as a tool to understand human intelligence. Here you see some humanoid robots. Some of them are well known. For instance, the leftmost, Asimo. This is the newest, few days ago, Honda announced the research Asimo that is a little bit larger and faster than the previous model. It has more degrees of freedom, and it can not only walk, but something like jogging. The next one from Sony is called Curio. This is for entertainment. It's smaller, but it looks more refined, and it looks like it would almost be a product. So far, you cannot buy it, and Sony doesn't announce when, if at all, and when you can buy it. H7 is a university project. HRP2P comes from a research institute in Japan. Then Sylph has been built by an individual person. It's pretty small, but it has many degrees of freedom, and it's quite impressive. And the last one is from Germany, from Munich, called Johnny. It's walking pretty nicely, and it's the largest one of these robots. But there are not only projects that deal with entire humanoid robots, but also with heads, for instance, for communication. The first one you see that can smell, and Kismet, the second from the right, is very well known, has been used to investigate social behavior of robots. And there's also a couple of projects that deal with manipulation. Here, arms and hands are the main focus, and very well known at MIT, for instance, is Cog, that is playing with a toy there. And here in Germany, in Karlsruhe, there's Arma that is supposed to tidy your dishes and clean your kitchen. And there are two hands in the pictures from the DLR and Forschungszentrum Karlsruhe. So there has been quite a history in humanoid robot research, especially in Japan. There at the Waseda University since 1973, last century, and they still produce impressive heads and robots. Also, industry spent a lot of money, namely Honda with Asimo, Sony with the Curio. Recently, Toyota announced this trumpet player that is in the picture, and they want to show it at the Expo 2005 exhibition. There are also some crazy project proposals, like the Atom project that can only come from Japan. This project proposal has a time frame of 30 years, and the idea was to build a robot capable with physically and mentally comparable to a 5-year-old boy, and this is a pretty tough challenge. There are some projects in the US as well, mostly at the MIT, Cog, Kismet, and Leo, and at the CMU, Carnegie Mellon, with the NERSPOT project. And in Germany, Johnny you already saw, and Amma. The Maxi head has been built in Paderborn. DLR builds hands and lightweight arms. There's a Hermes, pretty heavy robot, built by the Bundeswehr, and many other projects that I cannot mention here. Yeah, this is to give you some impression of the RoboCup competition. It's not only about soccer, there's rescue as well, and junior competition. The soccer competitions take place in several leagues, including simulation, where you can easily play 11 by 11 and have some team play. There's a small size league where the camera is above the field and looks at these color markers. These robots are pretty fast and can pass well. We have mid-sized league with larger autonomous robots. The Aibo dogs have a league of their own, and there is a new league for the humanoid robots. This humanoid league has been established in 2002, and it's just one step towards this long-term goal of the RoboCup Federation, namely to, by the year 2050, develop a team of fully autonomous humanoid robots that can win against the human world soccer champion team. So this is a pretty ambitious goal derived from the success with chess. And so far, there are only preliminary competitions, such as walking around the pole or penalty kicks, a free performance where you can do more or less anything, and technical challenges. First competition in the Humanoid League was held in Fukuoka. There were 10 teams, and I selected couple of robots here that participated. The Nagara robot, the second from the right, is the one that won overall this competition. Second competition was in Padua, 2003. There were only 7 teams because it was far away from Japan, but the Honda Asimo participated as a prototype and won this competition. This summer, the competition was in Lisbon. Here you see the participating robots, 13 teams, and the little green robot that won overall this competition. Our team, Nimbro, participated with 2 robots. On the left, Alpha, and standing in the middle is this Nimbro RS robot. And I want to show you a little bit more about technical details later. But first, give you an impression of the level of performance. This is the final in the H40 league. These are the smaller robots, and you see Vision versus Robo Erectors. And the Vision robot has a special... Yeah, this is a brave robot. These robots, they don't know any fear. Yeah, the Vision robot can look into all directions with an omnidirectional mirror, and so it can easily see the ball also from the side. And this time it was guessing the corner, but unfortunately it guessed the wrong corner. Or no, it guessed the right corner, but it was the wrong time. So this robot gets up, and Robo Erectors is able to score.
Robo Erectors went into a defensive position. Team Osaka has its goal target. Knows where the ball is, it's approaching the ball, pulling back and kicking, and it's a goal.
Yeah, I guess Robo Erectors is missing the last kick, and so the Vision robot won overall this competition. Okay, here you see the people of our team, Nimbro from Freiburg, who went to Lisbon, and in the middle 2 robots. The larger one is Alpha, and the smaller is an augmented, the Robo Sapien. The robot Alpha we started to build this spring, and it's not really finished yet. What you can see there is about this size, 155 centimeters, about 30 kilograms, and it has 21 degrees of freedom. These degrees of freedom are driven by geared DC motors. There are 6 in each leg, and 3 in each arm, and 3 in the trunk as well. So it's a pretty movable robot. Here you see it exposed, view on the mechanics. We built a skeleton from a carbon composite material to have it lightweight and also sturdy, and used geared DC motors from Faulhaber that we fitted into these carbon tubes and constructed the robot from that. The electronics that is needed to control the stuff is mainly a sub-notebook that has been selected for weight, and there are 11 small microcontroller boards distributed throughout the robot. They communicate via CAN bus with each other and with the main computer. We have some rechargeable batteries and power supply for the microcontrollers. You can see here this microcontroller board. Each board controls 2 DC motors, and there's a part for logics over here, and a motor driver part over here for 1 motor each. We have instrumental amplifiers, a little bit user interface, a little bit communication as well. Tasks for this microcontroller are to actually do motion control. So they measure the position and speed of the motors and regulate this with pulse width modulated switching on and switching off the motors and changing turning direction. CAN communication is also done with the PC at the rate of 60 Hertz. It reports the state of the local joint to the main computer and receives new targets for the control loop. And there's also some pre-processing done of sensory signals. What kind of sensors are on the robot? Well, there's a pair of stereo cameras. They deliver an uncompressed image via FireWire, but they are not attached to the microcontrollers. They're attached directly to the PC. Then we have tilt sensors, namely accelerometers and gyros, force sensors on the feet, and encoders and potentiometers to measure the motion of the motors. If you want to build a biped robot, you may want to know how it is tilted in space. And one way to find out about this is to use a combination of accelerometers and gyros. If the accelerometer is not moving, you can basically measure gravity and decompose this into two axes, and you know how your accelerometer is tilted. But if it's also moving, you have these linear accelerations, and you cannot really distinguish between the two. The gyro reports rotational speed. This is also a good hint about the tilt, but you need to integrate this, and you need to start somewhere. And so we came up with the method of calibrating the gyro, which also reports that it's moving when it's actually not moving, using the long-term accelerometer readings. And here you can see the result of this data fusion. The black, for one axis, the black curve is the acceleration measured, the green curve is rotational speed, and this sensor was moved like this to the vertical, and then moved like this. The red curve is diffuse tilt, and then it was moved linearly back and forth. And you see that you have a lot of acceleration, linear acceleration that you measure, but this doesn't go through to diffused tilt estimate. For behavior control, we use a framework that has been developed at FU Berlin in the group of Professor Rojas, who was giving a talk before me. This framework supports a hierarchy of reactive behaviors. So the idea is to decompose a complex control tasks into many smaller ones and to arrange them in a framework that hopefully makes things easier. So there's a time hierarchy. We have quick primitive behaviors running at 60 Hertz, and the slower they get, the more complex they may become. There's an agent hierarchy, namely the entire body of the robot, body parts like a leg, and then the individual joints. And this modular design forces one to formulate abstract interfaces. Say, I might have an idea what an individual joint is doing, but I need to come up with a language what the entire leg is doing. So we decided, for instance, to parameterize this using the leg extension, changing just the length by coordinate movement of these three joints, and then on another axis we would change the leg angle relative to the hip plate, but keep the foot parallel to the hip plate, and then we would have the offset to this parallel foot. And so we hope that through this decomposition into small manageable units, we reduce complexity, and of course this also reduces interaction, this framework. The framework supports logging of all variables, so you can after the fact look at things, what happened if they don't go well, or even if they do go well. We have some 3D visualization, and we have also a simulated robot, so we can develop behaviors without using real hardware. We use the Open Dynamics engine for this physics-based simulation. You see Alpha competing in the freestyle competition in Lisbon this year, and we got the third prize for this. We tried to make it move somewhat rhythmically to the music. And this robot is not only intended for this RoboCup competition, but we also want to investigate multimodal communication with it. And we continued working on alpha, improving individual joints, but we also developed a head. It's not really finished, but it moves somewhat. Right now it has 16 degrees of freedom. It can, with 3 degrees of freedom, move the 2 cameras. It has a movable neck with 3 degrees of freedom. It can move the eyebrows at 2 positions, and it has 6 degrees of freedom to move the mouth. To implement this multimodal dialogue system, we use the OpenCV library to implement face localization and face tracking. We maintain a list of the closest persons around the robot, even though the robot is not looking at these persons. And we implemented some speech recognition using Novotech. It's a commercial tool. There's some self-written dialogue management, finite state machine, speech synthesis with text-to-faux and Ambrola, and we implemented some software to control the gaze of the robot, namely saccades and smooth pursuit motions, and we implemented head control and also animated the mouth while the robot is synthesizing sound. Here you see a video where the robot is engaging in a conversation with 1 person first and then 2 persons. Maybe we can have a little bit more sound.
Erzähl mir doch was über dich.
Unfortunately, the conversation is in German.
Momentan habe ich 36 Freiheitsgrade.
You see not only cameras moving, but also the entire head after a while. You see sometimes in smaller windows on the screen what these cameras actually see. So red square means that this face is really tracked and everything is fine. Sometimes it's green because once in a while the robot checks if some other person appears and looks nicer than Felix in this image. The conversation is about other robots, these ones, and about the Alpha robot itself.
Ja.
Soll ich denn jetzt etwas machen? Wo seid ihr? Oder etwas über Toni erzählen?
Erzähl doch was über Toni.
Toni ist unser neuester Roboter. Er wird von 12 Servomotoren gesteuert. Er ist 54 cm groß und läuft im Moment mit bis zu 16,5 cm pro Sekunde. Er kann autonom agieren, da er mit einer Batterie durch einen Pocket G10-Kamera ausgestattet ist. Wollen Sie noch mehr erfahren?
Ja.
Da Toni eines Tages Fußball spielen soll, wurde er nach dem Colorado benannt. Besteht noch Interesse an einem anderen Roboter?
Nö. Wie viel Uhr ist es?
Es ist 16:31 Uhr.
Danke. Und wo ist der Ausgang?
Im Erdgeschoss. Sie können die Treppe unter dem Aufzug benutzen.
Now with 2 persons.
Wollen Sie etwas über die Roboter erfahren?
Ja.
Über was wollen Sie
One task now is to decide which person is the most salient one, and so the robot makes sure that it's facing the most salient person, but once in a while it looks at the other person if the other person is still there.
Der Pocket G10 kommuniziert über eine Infrarotschnittstelle mit dem Roboter. Wollen Sie noch
It's a bit
mehr
nervous.
erfahren?
Ja.
Am Sendbuch ermessen haben wir 2004 an der Eurocup 2004 Humanoid Robots Competition teil. In der Technical Challenge konnten wir den 3. Platz erlangen. Möchten Sie noch etwas über einen anderen Roboter erfahren?
Ja.
We did not implement sound source localization, so Mario moves closer to the robot to draw its attention.
Der Konto.
Konto ist unser kleinster Roboter. Wir wollen einen Roboter für Reichmann und Köder.
Looks like Phoenix 1.
Momentan kann ich an 10 cm pro Sekunde laufen.
Okay, this is under construction. We want to improve on the mimics and work on expression of emotions, and of course we would like to integrate this head with the robot body. We also think about actuated hands to allow for pointing gestures, and the final application will be the use as a museum guide. The next robot I would like to talk about is RoboSapien. We had a robot like this in Lisbon, and you can buy this in a toy store. It has been developed by Mark Tilden and produced by Huawei Corporation. Has only 7 degrees of freedom, and 3 are used for this kind of dynamic walking that you see in the videos. This is a toy, and you can control it with a remote control. But to make this autonomous and programmable, we added a little bit more hardware to it. This Pocket PC here, and attached to the Pocket PC is a CF camera that we use to watch what is in the world, to do behavior control and send commands via infrared to the robot base. You see the robot competing in the technical challenge this year in Lisbon, the RoboCup competition. The task was to walk across this sloped ramp, and we implemented some green detection to make sure the robot doesn't fall off the sides of the ramp, and we also try to detect the yellow lines that indicate change of slope to adapt the gate to these new conditions. And only 2 teams, including us, were able to manage this challenge. And there was another competition called Humanoid Walk, where the task in the lower video, the task was to walk around this orange pole. And during the competition, we kind of lost track of the pole, but we worked on this in our lab. So now the robot turns around, looks where the pole is, knows now where it is, and can continue its walk. We put the API that shows you how to capture images with the robot and how to send motion commands to it on the web, and got /dotted for this. Now we have a couple of these robots. Also, we kept the arms because now we have a little smaller Pocket PC. Changed the camera a bit by adding a wide-angle lens. The image you can see in the lower right corner. And the intention is that we play real soccer games at next year's German Open with another team from Osnabrück who are doing the same. In a student lab, we develop computer vision, behavior control, and infrastructure software to control these soccer-playing robots, and it's going to look like the training picture here. So far, they are not really playing soccer, but we implemented some behavior for a field player who tries to move the ball towards this blue goal, and for a goalie who tries to prevent that from happening. So these robots have an advantage because the low center of gravity, they are pretty stable. You cannot make them fall, actually. And they are cheap, so you can get many of them without much effort, but they are limited too. One limitation, for instance, is they cannot walk towards the side. They can just walk straight and back and turn. And so you have to do a lot of navigation to go behind the ball such that the ball is in front of you and you can kick it into the goal. Well, kick is also a limitation. The robot cannot really kick. It just walks through the ball and moves the ball a little bit. This is all not very reliable, but hopefully the robot will succeed in this endeavor. Yeah, the goalie doesn't do much. it just turns towards the ball, and if the ball is close, it tries to push it away. But if a hard kick comes like this one here, the goalie is without chance. Yeah, the last seconds show the goalie a little bit more engaged. Yeah, robot and robot fight will be a big problem. These robots have actually touch sensors on the fingers and on their feet, so they stop moving if they touch something. But we have just one-way communication, so our behavior control software doesn't really know about this collision. And we don't have obstacle avoidance yet, I must admit. If you build humanoid robots that walk on two legs, dynamic walking is really a problem. And as far as I see it, there are two main approaches to it. One is the one taken by, for instance, Honda Asimo. This starts from static stability. If my center of gravity is within my area of support, I do not fall, and you can extend this to moving bodies. This is called zero moment point or center of pressure, and you need a good model of your robot, and you need a lot of computing power to do that. But obviously it kind of works, but it looks like a robot, especially if you compare it to the young lady. The young lady is much more relaxed and much more elegant than the robot, who walks also while bending its knees like this. Another approach is to start from dynamic stability. So there are a couple of machines that can do passive dynamic walking without any actuation, without energy, without motors, without control. They walk down a sloped surface. And this is very elegant, I think, and it's extremely energy efficient, but it's not statically stable. They cannot stand, they can just dynamically walk. And here in the lower video you see a version that can walk on flat surfaces with minimal actuation. So this is like a pendulum, and you give it a little bit a swing for each step. Actually, in this case, when one leg hits the ground, there is a little push with the other leg that you can see here. You can see the push. And this is very nice, but I think we need both. We need energy efficient and elegant walking, but of course the robot should also be able to stand. This video shows this little guy. This is a construction kit we got from Japan. The company who makes this is named Kondo, and so we call it our Kondo robot. It's driven by 17 servos, 5 for each leg and 3 for each arm, and also a movable head. It's small and lightweight and can be controlled with a serial interface. You get some motion control software from the company, and it's energy autonomous, so it has a battery. We went ahead and made this autonomous by adding a pocket PC with a camera, this time with a serial interface. Where is it? Okay. We reverse engineered the serial protocol and implemented our own behavior control software with a rate of 50 Hertz. You can see here preliminary walking experiments. We walk with quick, small steps to use the dynamics of the robot. And a student is working on the thesis right now to implement automatic optimization of this gait pattern. And the last robot I want to talk about is Tony. This is also our latest construction. Technically, it's similar to the Kondo robot. So there are 18 servos that drive individual joints. We have 6 joints in each leg and 3 joints in each arm. It is 74 centimeters high and only 2.2 kilograms, so we tried very hard to make it lightweight, because then you need smaller motors, and it's not that dangerous if your robot falls. There are 3 little microcontroller boards distributed in the legs and in the trunk, and they communicate via CAN bus and with a serial line to a pocket PC, which is equipped again with a camera. This time the control loop frequency is 167 Hertz. We also have an attitude sensor with accelerometers and gyros, and we selected lithium polymer batteries because they are lightweight. Here's the preliminary walking experiments. In the meanwhile, we had it walking faster, and we added another degree of freedom and improved the arms. Here you see the toes joint in action. So it can balance on its toes. But that was not the purpose why we built this. We built this actually to do this, to make the leg longer than it actually would be in the situation where we shift weight to the other leg. We started playing with omnidirectional walking. So the idea is that the robot shouldn't only be able to walk, but also to start the motion and stop it again without falling, and to change the direction of motion. So this sequence is straight walking, and it can walk towards the side as well. And it can walk not only forward, but towards the back. It should not change its orientation during these motions, and independently from moving it forward and to the sides, we started working on changing the orientation of the robot. And so far, you can blend these walking directions smoothly into each other. That's what you can see here. It starts moving to the side and then moves more and more to the front, and then more and more to the other side. We also closed the loop by using the camera image to detect the ball in this case, and give the information of relative ball distance and angle to some very primitive behavior. The behavior tries to get behind the ball, and if the robot is behind the ball, then it starts walking towards the ball. So it's dribbling it a little bit. And of course, this is very slow, but these are the first experiments, and we are confident that we can improve on this. We have actually the choice. Development is done on a PC, and we can send motion commands to the robot via a serial line. This is faster for debugging, but we can also download the program on the Pocket PC, execute it there, and then the robot is fully autonomous. Energy supply is autonomous, and the image processing, behavior control is autonomous. So it happens more or less by accident that the ball goes into the goal here. We do see the goal, but we didn't use it in this experiment. Our plan for Tony is to add some more sensors, like force sensors on the feet and the compass, and also to build smaller versions for the RoboCup competitions. We have to adhere the rules of this competition, and they say it has to be smaller than 60 centimeter. But there's also another league for larger robots, and they can build robots tall up to 180 centimeters, and we would like to try to use more or less the same technology to build a larger robot. With regards to soccer, we think, of course, about kicking, and we are working on self-localization. We need to control the ball, to implement some team play, because this year in Osaka, and getting up after falling, this year in Osaka there will be the first real games in such a competition. 2-on-2 games are planned for smaller robots. Here you see the outline, the floor plan of the hall where the competition is going to take place, and the organizers think that about 200,000 people will come. And I think this is a realistic estimate, because more than half of this came to the competitions in Fukuoka in 2002. In conclusion, I think it's not only fun, but also an interesting research area to work with humanoid robots. And each individual technical component may not be that difficult or challenging, but you have to make that system work, and it's a quite complex integration task. So mechanics and electronics and behavior control and computer vision all have to come together and work at the spot, and usually the weakest component is the one that determines performance. Hopefully such an integrated system will be more than the sum of each parts. We hope that we can show some synergy effects. Think of, for instance, audiovisual speech recognition, where you could listen more closely if you see a talking mouth, or you could direct your ears towards a sound source that you localized, and then you see also better this person. Also active perception is a good example for synergy effects. You can try to reason a long time about what could be behind this desk, but if I can do active perception, I can go there and just look what is there. And also that usually for controlling behavior you don't need a perfect reconstruction of the world. Few key features, stimuli, usually suffice to control the behavior in an acceptable way. Of course, Hollywood is already a step ahead. Some of you might have seen the movie iRobot, with this very advanced NS5 robots that do a lot of the tasks that I mentioned on my first slides for motivation. I guess we need some sort of artificial muscle. So far, the driving units for the gears are not very satisfactory to me. Especially the gears are kind of heavy, and they do not deliver that much torque that one would hope. Of course, lightweight frames and soft covers are needed. Energy supply is the key. You want to operate such a robot not only for 10 minutes, but a couple of hours, an entire day. Control needs to be very robust, so that there is like an emergency behavior for every possible situation that could come up. And it's quite a challenge to manage the complexity of the high number of degrees of freedom of these robots. Perception is difficult in the world where the stimuli are ambiguous, not as clear as an orange ball on a green field. And learning would be nice, and team coordination. Of course, the long-term vision is that there will be such personal robots, and there are a couple of people who share this vision, including here the vice president of Sony, who said in 30 years, I think and he was talking about the personal robot industry, will be bigger than the personal computer industry. We need to do more research, however, into movement, but also into intelligence. And this motivation for us. Here are the people of our team Nimbro, University of Freiburg. Maren Benewitz is here, as well as Michael Schreiber. Working full-time also on the project is Jürgen Müller, and there are a couple of students who work on different parts of the project, like building the robots, Michael, or implementing computer vision, or doing behavior control, or also on tools to program the microcontrollers. We got some help from other groups, namely Alexander Kleiner from the group of Professor Nebel in Freiburg helped us with setting up a simulation environment, and Dr. Achim Liers from FU Berlin helped us with designing the electronic board for the microcontrollers. Yeah, I am ready to take some questions, but I would like to draw your attention also to the demo in the hall, where we hopefully can show these robots in action. It's a bit hidden. We used to be in the cafeteria, but there was a conflict with the video, with the VJs. And now we moved to a remote place. You have to go through the basement and through the hacker center, turn to the left, through the hacker center to the very end, and then up the stairs. There's a hall where you can find the robots. And if this description is a little bit too difficult, you can try to follow me after the talk, and then you might be able to find it. But in the meanwhile, we should use the time for questions.
Eine kurze Frage. Für den netten, süßen, wie heißt der, iRobot, der erste?
The first one is
RoboSapien. Have you planned to give the community your work back or to the community to modify the RoboSapien?
As I mentioned in the talk, we put a little document on our webpage. This is www.nimbro.net that describes how to cut this hole and how to extend the receiver, and most importantly, there is an API for accessing images of the camera and for sending behavior control comments, motion control comments to the robot. So this is already accessible. More questions? There was a question about money. You can buy this robot for about 100 euros everywhere in toy stores, and you can buy this robot without pocket PC and camera for about 1,000 euros. It comes in pieces. It's a construction kit, and you have to import it yourself from Japan. This one, Tony, is constructed in our lab, and it's a little bit more effort to build another one. But we will build smaller versions and maybe also larger versions of it. More questions? Well, then I thank you very much for your attention.